Hi guys, and welcome to SA3 Populations versus Samples. I'm Mrs. Avila, and I'm going to be helping you guys out today. If you don't already have a copy of the notes printed out, please do so now, or get out a sheet of binder paper so that you can jot down some important information as we work our way through this. All right, we have three key objectives today: identifying populations versus samples in the context of a scenario, identifying parameters versus statistics in the context of a scenario, and comparing simulation results to a hypothesis to determine evidence for or against a claim. All right, so let's start off with populations versus samples. A population is the collection of all data, such as responses, measurements, or counts, that you want information about, okay? Now, populations oftentimes are very challenging to get information from because you're typically trying to learn about some really large groups of peoples or things. One way you can kind of think about it is the population is the who or the what you're really trying to learn about. So I might be trying to learn about all US adults. That's a really large group of people, and so I'm going to probably find some challenges with getting information from all of them. That's why we have samples. A sample is a subset of a population of which you are able to collect information on. So maybe I'm trying to learn about all US adults, but I am actually able to interview 100 US adults. The 100 that I'm actually able to ask questions and get responses from, those would be the people that I would refer to as my sample. You can think of your sample as the who or the what you are actually able to collect information from. So why is it important that our sample is representative of the population we want to learn about? Well, when we sample, we're not necessarily getting the exact people or things, or at least not entirely, that we're trying to learn about. If our sample is not representative of the population, what that means is that any conclusions or measurements that I get from that sample might not actually make sense to make a claim that it represents the larger group of people or things in my population. So if I only am able to sample US adults in Livermore and I'm trying to learn about all US adults in the entire country, that sample's probably not going to really help me learn about the population that I want to, because it in itself doesn't represent all US adults. Drawing conclusions about populations is one of the main goals of statistics. It plays a role in something we call inference, which we will talk a little bit about later on in this unit, but it's a big topic in the statistical community. So let's try identifying populations and samples. So we're going to identify the population and the sample and describe the sample as specifically as we can. We're going to do two examples, and then I have a couple of U-tries that you can pause the video and take a look at. Example 1, the owner of a dance studio asks 32 dancers what their favorite type of dance is, and 25 say hip-hop. So the population is, who in general am I trying to learn about? I'm trying to really learn about all dancers in the studio. However, the people I'm actually able to get information from, my sample, is the 32 dancers in the survey. Specifically, of those 32 dancers, the sample consisted of 25 dancers who said hip-hop, and the others did not. Okay, so notice my sample is who I actually got information from. My population is who, kind of the big picture I'm trying to learn about. You'll notice that the word all is oftentimes a part of describing a population. All right, example number 2. A counselor at Easton Middle School pulled 225 student class schedules and found that 46 students have science first period. Again, the population is who overall I'm trying to learn about. In this case, I'm trying to learn about all students at Easton Middle School. Again, you notice that word all is there. My sample, however, is the 225 students whose schedules I actually was able to pull and gather information from. Now, to describe the sample a little bit more specifically, I can say that the sample happened to consist of 46 students who have science first period and 179 do not. All right, so we had a couple U-tries that you can go ahead and pause the video and take a look at and reference the key if you want to check your answers. Now we're going to move on to the difference between parameters versus statistics. Parameters and statistics are very similar in that they're both a numerical measurement. However, a numerical description of a population specifically we refer to as a parameter, and if we have a number that is describing a sample, we call that a statistic. A little simple way to remember that is the S's go together and the P's go together. Samples have statistics, populations have parameters. Because some populations are so large to measure, a statistic such as a sample mean or a sample proportion can be used to at least estimate the parameter, such as the true population mean or the true population proportion. Basically, it's really hard to gather data from populations because sometimes they're really big, so we'll use samples and therefore statistical measurements in order to estimate about them. All right, so let's try and identify some parameters in statistics. Okay. Example 1. For all teens in a certain town working jobs last summer, the mean hourly wage was $6.95. Is the mean wage a parameter or statistic? Explain your reasoning. Basically, we need to decide, does that measurement of $6.95, does that represent the population or only a sample or a subset of the population? Here I would say parameter. Because the $6.95 is based on all teenagers in town who worked last summer, it's not referencing only a subgroup of the teenagers, it's referencing all of them. So that's the entire population of teens. Example number 2. A survey of 912 men aged 50 to 60 in Central America found that the standard deviation of the length of their feet is about 4 centimeters. What is the standard deviation of foot length, a parameter or a statistic? Explain your reasoning. Well, we have to decide, is that measurement of 4 centimeters, is that about the population or only a subset of the population? In this case, I would say it's a statistic because there are more than 912 men ages 50 to 60 in Central America, so this measurement is based on a subset. So now you can go ahead and try the 2 U-tries that you have on your paper. Again, we're trying to decide if it's a parameter or a statistic, and then why you would believe that it's one or the other. All right, so that brings us to our last topic, which is hypotheses. In statistics, a hypothesis is a claim about a characteristic about a population. Here's some examples. A drug company claims that patients using its weight loss drug lose an average of 24 pounds in the first 3 months. That's a claim. We don't know if it's true or not, but it's a claim by the company. A medical researcher claims the proportion of U.S. adults living with one or more chronic conditions, such as high blood pressure, is 45%. It's a claim by a medical researcher. We don't know for sure if it's true, at least not until we were able to collect some information. So in statistics, a hypothesis is a claim about a characteristic of a population. To analyze a hypothesis, you need to distinguish between results that can easily occur by chance and results that are highly unlikely to occur by chance. If you ever see an outcome actually occur and it should have been super unlikely to have happened by chance, typically that actually means that the hypothesis was probably false to begin with. One way to analyze a hypothesis is to perform a simulation. When the results are highly unlikely to occur, the hypothesis is probably false. So let's talk about me and basketball. So here's a little example to hopefully explain what I mean by hypothesis testing. Let's say I, Mrs. Avila, make a claim that I'm surprisingly really great at basketball. In fact, I not only tell you that I'm great at basketball, but I tell you that I am so good that I actually have a about 5 out of 6 rate, 83% free throw success rate. The question is, would you believe my claim? Okay, so let's say maybe later on you find me and some other teachers in the gym and we're playing basketball. And you sit down and watch the game a bit and you notice that I actually only made 4 out of 10 baskets, 4 out of 10 free throws. So prior to seeing this, I told you that I make 83% of my free throws. And then you watch me in the game and I only make 40%. The question is, well, what do you think about my claim now? Do you believe my hypothesis, the claim that I made at the beginning, I'm an 83% free throw maker? Do you believe that claim? Kind of why or why not? Okay. The fact that I if I claim 83% success rate of making free throws, the fact that if that were true, I should rarely only make 4 out of 10 free throws, but it actually happened. Like, you saw me only make 4 out of 10 free throws. Seeing something that should have been unlikely to occur, given the claim to be true, probably starts to put some doubt in your head about the claim to begin with. Okay, for instance, in this case, seeing me only make 40% of my free throws probably makes you start to doubt whether my claim of 83% success rate probably isn't real. Probably my claim was false to begin with. That's hypothesis testing. All right, so let's look at a couple examples. Let's say you roll a 6-sided die 5 times and you do not get an even number. This seems super weird, so you start to suspect that maybe the die favors odd numbers, not evens. Now, the die maker, the company that actually made the 6-sided die, claims that the die does not favor odds. So what is this claim that we are kind of starting off by trusting the company about? Basically, the company is saying that they believe that the die is fair, meaning it doesn't favor evens, it doesn't favor odds. Ultimately, it should be about 50-50. All right, so let's say we have this claim by the company and we want to see whether our die follows that claim. So one thing we can do is we can run a simulation. A simulation is a way that you could use either physical objects or maybe even a computer to represent something happening many, many, many times. So what we have here is I ran a simulation of a just standard 6-sided dice and rolling it a total of 50 times. Now, this histogram that we have here, it's not a single set of 50 rolls. Basically, this is a histogram displaying rolling a die 50 times, many, many, many times, okay? So what we want to do is we want to use these results as our way of gauging whether we believe the company's claim or not. Okay, now, basically what this histogram shows is these are the types of results that we should expect to see if we really do have a legit 50-50 die, meaning 50% odds, 50% evens. So basically what this shows you is you will see some variability. Not every time I roll a fair die am I going to get exactly 25 evens, 25 odds. That's not going to happen. But you should notice a lot of your results center around about 50-50 evens and odds. And every once in a while you get kind of those odd samples. Like down here all the way to the left, it shows that I did 50 rolls and I just happened to get only 30% odd numbers, which would mean 70% evens. So it's not likely that that would happen, but it is possible. Okay, so if you look here, getting 46, so if you look at 0.46 on this x-axis, 46% odds, we can see that that happened about 8% of these simulation results. That could totally happen. 8%, that's almost like 1 out of every 10 times it's going to happen. Okay, so we're going to use these simulation results, and it says, what should you conclude when you roll the die 50 times? And let's say you happen to get 26 odd numbers. So I look at my histogram, and the claim is that the die is 50-50. I'm going to look at what 26 out of 50 rolls would be, and that ends up being 52%. So this is saying I rolled it 50 times, I got 52% odds. So if I look at my histogram here, the highest bar, in fact, right between 0.5 and 0.54, that's 52% odds. If you look at the height of that bar, that means that that outcome happened a bunch of times. Okay, so what I can say is because this type of result would happen probably about 16% of the time with a fair die, and it happened with this die in particular that I'm trying to decide about, that seems pretty likely, which means the die maker's claim could very likely be true with a result like that happening. What if I were to roll my die and I got 35 odds? Now, 35 out of 50 is a little bit different of a proportion. In fact, 35 out of 50 is 70% odds. So if I go all the way to the right on my histogram, 0.7, basically what what we're saying is we did this simulation of rolling a fair die a bunch of times, and never once did we get 70% odds. But then I rolled this die and I did. Maybe that makes me start to question, maybe this six-sided dice, maybe it's funky. Like, maybe it's not fair. Okay, so the fact that that type of outcome would rarely occur by chance, and I can tell because the histogram tells me what types of results I should expect, with the claim being correct. The fact that that would rarely happen by chance, but it did with my die, makes me think that the claim by the die maker, maybe they're false. Maybe this die is funky. Go ahead and try applying this idea to these two U-tries. Feel free to check the key, and we're going to do one last example to wrap this up. So now I have a dot plot instead of a histogram and a little bit different of a context. This says a national polling company claims 34% of US adults say mathematics is the most valuable subject learned in school. The survey of a random sample of 50 adults was taken, and this dot plot represents polling 50 adults at a time, and the proportion of them that agreed with this statement, the saying math is the most important. All right, so the claim is 34% of adults say mathematics. This simulation, this dot plot, represents the type of survey results we would expect to see with that claim being correct. Again, notice they're all centered around that claimed 34%. But even if the claim is correct, we would anticipate to have some groups of 50 people say a little bit higher or lower percentages. The question here is, what can you conclude about the accuracy of the claim that the population proportion is 0.34 if you survey 50 people and 15 of them agree with the statement mathematics is the most valuable subject? Well, 15 out of 50 is 30%. If I look at my simulation results, 30% agreement rate from a sample of 50, it looks like that could happen quite a few times. In fact, it happened 7 times. The fact it happened repeatedly with my simulation means that I could expect it to happen in real life as well. So I would say the company's claim very likely could be true. What about that same idea, but I survey 50 adults and 25% of them say that math is the most valuable subject? Now, looking at my simulation results, 25 out of 50 is 50%, so I go all the way to the right over here. What that one little red dot tells me is that it is possible that the company's claim of 34% being the correct proportion, it is possible that that is true, and I just happen to get one of these kind of weird samples that's unusually high. But the fact it doesn't happen repeatedly or very often makes me start to think that it probably would be unlikely to happen by chance. So what I'm going to say here is that the company's claim is likely false. Getting this type of result only happened once in our simulation, and because it didn't happen very often, makes me start to wonder if the company's claim was correct to begin with, or maybe the proportion is different than they claimed. All right, so we learned about population, samples, parameters, statistics, and wrapped it up with some hypothesis testing. Please make some notes in regards to any questions that you have, and then either reach out to myself or Mr. Hahn, Ms. Jeffries, and we are happy to help you out. Otherwise, I hope you have a great day and look forward to seeing you on our next Zoom call.